Okay, in this video we're going to be looking at a bit of an overview of Lewis structures. We're going to very quickly look at what we did last year, and we're going to build onto that for how you do Lewis structures that don't obey the octet rule because they are more common this year, and Lewis structures of ions because they're also an important new thing for this year. So the first thing I want to look at is what Lewis structures are, or Lewis diagrams are, and the way you did them last year. So last year you would have known that the dots in a valence on a Lewis structure, or the crosses, if you draw them that way, show the valence electrons for that atom. And you were trying to obey the octet rule for every element apart from hydrogen and boron, basically, and unless an ionic compound is forming. Of course, things like lithium and magnesium and some of those things that become ions, they don't obey the octet rule because they transfer their electrons to the other element to make ions. So we're really looking at covalent compounds, or, as we're going to find out today, polyatomic ions. Poly meaning atomic, so many atom ions, like SO4 2-, NO3-, that sort of thing. Alright, so going to very quickly go through ammonia and how we do the Lewis structure for that. And what we do is we very quickly add up how many valence electrons we've got, 1 for each hydrogen, and 5 for nitrogen. And we're going to put those together, and from that we can look at its shape and work out if it's a polar molecule or not, basically from those ideas. So we put all of that together. This one's quite an easy one to look at. If we're trying to obey the octet rule for nitrogen, it's got 5, so it needs 3 more electrons. And we can see we've got 1, 2, 3 more electrons there. So let's put those electrons in there. Well, they take the hydrogen with them and make a covalent bond. So we have that. Now what you'll find is that at level 3 we prefer you to take any paired electrons out and replace them with a line to represent a single covalent bond. So that would be our Lewis structure for ammonia. Okay. I'm going to very quickly look at another one. I'm not going to use the dots for this one. And carbon dioxide. Alright, so have a look at another one. So carbon has got 4 valence electrons. I will use the dots for carbon though, actually. Okay, and oxygen has got 6. Now I'm going to not use the dots for these because I'll run out. Okay, so I can see that each oxygen needs 2 more. But actually the easiest way to start doing one of these is just to draw the chemical bond between these and see what we've got left. So if I draw that chemical bond in, still got the right number of electrons, but this carbon's only got 1, 2, 3, 4, 5, 6, and each oxygen's only got 7. So what we do then is we bring these 2 electrons in here to make a double bond, and these 2 electrons into here to make a double bond. Alright, so those are the ones from last year, and if you want to look at my other video on Lewis diagrams at level 2, you'll get a bit more information on that. What we want to look at in this video are the ones that don't obey the octet rule, and give you a bit of an overview on that. What we find is that we're going to have to do Lewis diagrams for things like phosphorus pentachloride. Now already by its name, PCl5, we can see that the phosphorus is going to need to be bound to 5 chlorines, which is 5 chemical bonds means 10 electrons. So automatically we can see that that's not going to obey the octet rule. So if we have a look at the number of valence electrons here, we've got 5 from phosphorus, and 5 times 7 from chlorine is 35. So we're going to have 40 electrons in this. So how do I do this? Well, first thing is exactly the inference I said before. If it's got 5 chlorines, they're all going to be bound to the phosphorus. So I'm going to draw my phosphorus, and then I'm going to have 5 chemical bonds coming off it, each of those with a chlorine. And just accept that it's breaking the octet rule. And then I'm going to fill in the electron configuration of the chlorine so that each chlorine is obeying the octet rule. Then I want to add them all up and see if I get to 40. If I don't, then I've got to do something else. But not surprisingly, for teaching a concept, I've chosen an easy one to start with. If I add all of these up, 2, 4, 6, 8, don't forget that the bond is worth 2. Well, 8 around each chlorine, 8 times 5 is 40. That's worked. The reason, simplistically here, the reason that phosphorus can do this is that it's got electrons in the third energy level, which means it can actually start using more than just its S and its P orbital. So it's got a bit more space in there to actually create these chemical bonds. Alright? Okay, so that's one example there where we've got the octet rule being broken because it's not, you can't fit in the 10 electrons, 10 bonding electrons around 2 different atoms. You just can't do it. The valency of chlorine is 1, so obviously they can only make 1 bond each in this case. Alright, there's some other ones that are a bit funky as well. Other ones such as, I'm not going to draw them up, CO does some really interesting things, which you might have done last year, but one that breaks the octet rule, NO2, and we can see this quite easily by the number of electrons in it. Nitrogen's got 5 in its valence shell, and oxygen has got 6, so we've got 12 there. Somehow we've got to get 17 electrons in this. So again, we start the same way and go, well, nitrogen's going to be in the middle. Let's do a bond each side to an oxygen. And if I fill in all the spaces, I'll add up how many electrons I've got and see what happens. Okay, so I've filled it in, so all of them are obeying the octet rule. And I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I've got way too many. So the first thing I'm going to do is create a double bond somewhere like I would with sulfur dioxide. So I'm going to get rid of those 4 electrons to get me down to 16. Put my double bond in there, which takes me back up to 18. 18 is still too many, so what am I going to do? Well, usually you have a problem here, but we can with nitrogen, nitrogen's a special one, we can have that. Alright? And if you remember from equilibrium last year, NO2 is in an equilibrium with N2O4, which is a colourless gas. So that kind of shows us why they can bind together quite easily, because they'll obey the octet rule once they do that. Okay, the lone pair from this molecule and the lone pair from a neighbouring molecule will create a covalent bond. So that sort of shows why that works there. So nitrogen is a bit of a special case. It can actually get away with 7. If there's no other option, then nitrogen can get away with 7. Alright, so that'd be NO2. So that's how ones that break the octet, or an introduction to ones that break the octet rule. Either have 7 if it's nitrogen, or for things like phosphorus and sulfur, you can go beyond that. Iodine can go beyond it as well. So anything that can access those, basically d orbitals, to create bonding. Alright. The last thing we need to be able to do this year is to look at ions, and these are actually not that hard. They're the same as doing any molecules, but instead you've got to consider that they've either gained or lost electrons. So the first one I'm going to look at is I'm going to take this ammonia and turn it into the ammonium ion. And the ammonium ion has a 1+ charge. So what we would expect it to have is 5 plus 4 is 9 electrons. But the positive charge means that it has lost an electron in forming an ion. So it's actually 5 plus 4 times 1 minus 1 for that charge. So we end up with 8 electrons. And so it ends up being really easy to draw. Because if I do nitrogen with 4 hydrogens around it, 2, 4, 6, 8. I'm not quite done though. If I'm going to do a Lewis structure that has got a charge, I have to put square brackets around it. And at the top right of the square brackets, I have to put the charge. Now that ion is completed. Right, I'm going to wipe that one off, so I'm going to do a slightly harder one now. And this is one that I recommend you just learn, because it actually can be done to obey the octet rule but actually we've found from X-ray diffraction that it doesn't. And that's the sulfate ion. So, being 2 negative, it means it's got 2 extra electrons. So what we're looking at is 6 for the sulfur, 4 times 6 is 24, for the oxygens plus 2, so we've got, let's hope my maths is good enough here, 32 electrons. Now, if I draw a sulfur and put an oxygen around each of them, and then fill in these valence shells with the missing 6 electrons, they all have 8, that's 32 electrons. And that's awesome. And you'd expect that to be correct. This is one of the ones you just have to remember. It has 2 double bonds and 2 single bonds. Okay? And it still ends up having the correct number of electrons in this arrangement. So you can see the sulfur is blatantly breaking the octet rule. It's got 2, 4, 6, 8, 10, 12 electrons involved in covalent bonding in there. So it's breaking the rule. This is still not finished. This still wouldn't get me any marks because I haven't finished it off with the square brackets and the 2 minus. So Lewis structures are not much harder this year. We just want you to be aware that there are even more ones that break the octet rule. Okay? And sometimes do really funky stuff like nitrogen. And that you now have to do ions, and there's a special way to do the ions. Square brackets, charge at the top right hand corner. Alright?